Swayam Prabha. Digital India. Educated India.
Hello everyone, this is the fourth lecture of this week and today's topic is analysis of Euler-Bernoulli beam computer implementation. We have already discussed the theoretical basis of Euler-Bernoulli beam and its finite element formulation in one of the previous weeks. We will not discuss those things here. Rather, what we will do is we will take one example and then try to find out the solution using finite element method, and through the process we will again revisit the various steps in finite element method. Then at the end we will write a small program. Through that we can handle relatively larger problem with more number of elements and more number of nodes, and through that program we will also see what happens to the solution when we increase the number of elements. Okay. So let's start with a very brief review of what we know about Euler-Bernoulli beam element. So this is the beam element, and it has two nodes, and at every node we have 2 degrees of freedom, and total degrees of freedom is 4. And within this element, these degrees of freedom is approximated through the shape function. These are the shape function, and this is how the shape function looks. Okay. Now this is the element equation, element stiffness matrix, and then element load vector, and then this is element load vector and element displacement vector here. Element load vector had 2 parts. One is one part because of the distributed force if you have on the element, and this is that part, and if you have any concentrated force moment, then this will be taken in this part. So this distributed part can be approximated or can be represented within an element like this, where phi a are the shape functions and x bar y bar are the local coordinate system. Now let us rewrite these expression. This is the element level equation. This equation is the element level equation. Now let us rewrite this equation by replacing LE by 1 by h. This h is the length of the element, not just the length of the element, but next onwards wherever we have to refer to the size of the element, whether it is 1-dimensional problem or 2-dimensional or 3-dimensional problem. So h now onwards h will stand for the size of the element. Okay. Now if we substitute LE, the length of the element, by h, our equation is this. Okay. Now this is the equation we have. Now let's take an example problem. This is the example problem. Now the first step is the domain discretization. Let's do that. So first is domain discretization. This is our domain. Now suppose since in next 8-10 minutes we'll be doing manual calculation, and then we'll write the program. So for manual calculation we'll take only 2 elements. So there are 2 elements and 3 nodes, and these nodes are 1, 2 and 3. These 2 elements are element number 1 and element number 2, and then we have 1, 2 is the global degrees of freedom at element number 1 at node number 1, 3, 4 global degrees of freedom at node number 2, 5, 6 are the global degrees of freedom at node number 3. So 1, 3, 5 are the degrees of freedom associated with transverse deflection, and degrees of freedom 2, 4 and 6 are rotation. Now we also need to provide the connectivity of the elements. The element connected between 2 nodes. For element number 1, the connectivity is 1 and 2, means it is connected between node number 1 and 2. and for element number 2 it is connected between 2 and 3. This connectivity is important, as we also discussed in case of truss, because your results will not vary, but when you write the stiffness matrix and then assemble the stiffness matrices, this connectivity you have to keep in mind. And the size of each element is 2 and 2. Let us take EI constant for the entire beam. Now, once we have the discretization, next part is element formulation. Element formulation means writing the element stiffness matrix, writing the load vector, and then writing the relation between the element stiffness matrix, element degrees of freedom, and the load vector. So we know this is the element stiffness matrix for beam element, and if we write it for element number 1, this element number 1, it will be this. See, these 1 and 2, these are the global degrees of freedom. It indicates that element number 1 is connected between node number 1 and 2. So 1 and 2 are the global node number, and then 1, 2, 3, 4 in blue color, these are the global degrees of freedom. Similarly, for element number 2, this is connected between node number 2 and node number 3. And then the global degrees of freedom for element number 2 are 3, 4, 5 and 6. So similarly, we can write the load vector at the element level, and the element level load vector we have just now seen. This is the element level load vector. Now, for the distributed load, here it is uniformly distributed load. We know that if it is uniformly distributed load Q, if you substitute Q in this equation and then integrate over 0 to h, we will get an expression like this. Now, this is for the contribution of the distributed force, this part. So, for our problem, we have Q is equal to -10 and h is equal to 2. If we substitute that, our element level, this part load vector will be this. And again, these 1 and 2, red color 1 and 2, it indicates global node number. And for element number 2, this is the element load vector. Now we have element load vector and then element stiffness matrices. Then we need to assemble them based on the connectivity. Now let's assemble them. So let's first assemble the load vector. So these are the load vectors for 2 elements. We apply the same logic while assembling, even in case of beam. We have already discussed in detail the assembling part in last 2 lectures. Now let's do that. If we apply this, you see this is our global, there will be 6 degrees of freedom. So this F corresponding to the global load vector, the total load vector, and this will be what at node number, at node number 2, there will be contribution from element number 1 and there will be contribution from element number 2. So we have to add them, both the contribution we have to add. So this is the contribution from element number 1 and this is the contribution from element number 2. These are the contributions. Similarly, for nodal forces, you have a concentrated force and moment. These are the contribution from two elements, and this becomes the total global load vector. Now we can assemble now what we know about this we have now global load vector. Now equilibrium needs to be satisfied. What we know about the forces, we know that there will be a reaction VR here and MR here. And then at this point, at node number 3, we have a concentrated load 10 kilonewton and a moment 15 kilonewton. Now let us substitute that information in this vector. So if we compare this, then the Q1 will be VR and Q2 will be MR. If equilibrium at node number 1, if we satisfy, we get this. Now equilibrium at node number 2, if we satisfy, there is no additional extra load and extra moment or additional concentrated load and concentrated moment. At node number 2, we have a distributed load, but the distributed load is already taken in this part. So naturally this will be 0 and this will be 0. So similarly, if we satisfy equilibrium at node number 3, Q32 will be -10 and Q42 will be -15. So this will become our global load vector now. Now let's then get the global stiffness matrix. Global stiffness matrix is this. Again, the logic of assembling exactly the same. So this block is for element number 1 and this block is for element number 2, and their common node is node number 2, and this is the common node. This is to add this here. You have a contribution from both the element, and then finally our stiffness matrix will be this. And if we write the expression, our expression will be this. Finally, equation is this. Now, still this equation we cannot solve. We need to provide some constraint. Otherwise, we will see if we try to solve this equation, if we try to find out the determinant of this global stiffness matrix, it will be 0. It is a singular matrix. We have to provide some constraint. And what are the constraints we have in this problem? At node number 1, we have a fixed support. So, at node number 1, all these degrees of freedom are constrained. So, this will be 0 and this will be 0. If we substitute that in this equation, we have finally this. So, this is the final equation we have. This we can solve. But then before we solve it, we have to partition the matrices based on partition this equation based on the known and unknown information. And if we do that, okay, before that, what are the unknowns here? We have 3 displacement unknown, and then we have 2 force unknown. Okay, this will be VR, and this will be VR, and this will be MR. Now, we have already discussed how to partition this matrix, these equations based on the known and unknown information, and if we do that, finally this will give us these condensed equations, right? And the first equation we can use to determine the unknown displacement, because in this equation only this is unknown, all other information unknown. And once we have computed UU, the unknown displacement, that we can substitute in the second condensed equation to determine the unknown forces, right? Now, let us do that. So, this is the equation we have finally, and then if we take this part, then this part will give us this, and then if we solve it, then our unknown displacements will be this. And then we take the other part. Once we know the unknown displacement, these displacements are known. Now, next, let's take the other part. The other part will be this, and we substitute the unknown displacement here, and then finally, if we solve it, this will be the forces. And if we just, it is a statically determinate structure, and we can calculate the reactions and displacement, so we can compute it and find out that we can verify these results. Now, so here we stand. So, we have already determined the displacements, degrees of freedom at the node, and we have also determined the reactions, right? Now, let us compare whatever you have obtained with the results that we can obtain from strength of material approach. So, this is the comparison. Okay. So, these are the values we have, and this is the displacement we can compute from strength of material. This part is for the axial force, not for the tip load P. This part is for the distributed load Q, and this part is for the moment M. So, total displacement will be this. Now, this is the comparison. We see that looking at the comparison, it is very evident that the results that we have computed just now using finite element method and the results we can compute through the strength of material approach, they are same, and it is not surprising at all, because you see how have we computed these degrees of the nodal degrees of freedom and reactions. We have used in equations, and in that equations all the element level equations, element level matrices, element stiffness matrices, those matrices are exactly the same, the matrices that we have seen in direct stiffness method or matrix method of structured analysis. Okay, so that's why we essentially use the same set of equations to find out the solution, at least at the nodal level. Okay, so so that's why they match, right? But it will be interesting once we know the values at the node. It will be interesting to check, to do the similar comparison at a point other than the nodal points. Let's do that. So, here we have seen this at the nodal points, and if you can increase the number of element and then compute the displacement and rotations and compare those displacement and rotations with the analytical solution, you will see at the nodal point those values will match. Now, at the element level, within the element, how to find out the displacement? So, displacements within the element we can approximate through this shape function, and this approximation is this, right? So, if we take any element, say for instance, if we take element number 1, and within this element, in this element number 1, within this element at any point x bar, we can find out the transverse deformation like this. Similarly, at element number 2, at any point between 2 and 3, we can find out the displacement like this using the shape functions and the global degrees of freedom. Now, similarly, we can find out the say moment at any point at any arbitrary point. This is the equations anyway we know, and this W can be approximated as this, and when you substitute that W, our equations will be these, and these shape functions anyway we know. We can differentiate this shape function and then find out the moment at any arbitrary point within the element. Okay. Now, we will compute that what happens to this moment and then displacement within the element, and we will also compare those values with the value we can obtain from strength of material approach. But now take a pause and then write a small program. This is important because through that program we will see that if there is any error, if there is any mismatch between the finite element results and the results we can obtain from strength of material is at all any mismatch, how to remove, how to minimize that error, how to reduce that error. We will do that. Now, let's for the time being, now let's take this is the code. Okay, analysis of beam using finite element method. The structure of the code is almost same as the code that we have written for truss analysis, but since we have additional degrees of freedom, but different degrees of freedom, therefore our sum operations are slightly different. Okay. Now, so first is the this is the length of the beam, suppose, and this is the number of element is 1. Let's make it 2. Make it 2. And then h will be the length of the element, which is total length divided by number of node, and these nodal coordinates are this. Okay. Now, at the very beginning, let me tell you that this may not be the most efficient way of writing the program. Okay. The point here is not to develop a finite element code. The point here is to understand that whatever operations we have performed, whatever steps we have seen through manual calculation, those steps here we are translating into a small program. Okay. Now, and this is very important because when later on when you will be in industry, then you will use some commercial software or a special purpose software developed for that industry. But to understand finite element method, it is extremely important at least once in your life you write a small code and implement all the steps involved in finite element method. This is very important, and exactly that's what we are doing here. Now, this is the element connectivity. And then total number of node will be, this gives the total number node, this gives the total number element, and at every node we have 2 degrees of freedom. So, this is total number of degrees of freedom. Now, element properties, EI is constant in our example, that's why it is given as 1, 1, but final displacement, that what we get from this, that needs to be divided by EI. Okay. So, if we are taking a particular problem with particular E and I, we can substitute that. Boundary conditions. Now, at element number 1, at node number 1, we have 2 constraints. So, boundary conditions will be 0 and 0. 0 stands for it is constrained, and no constraint means 1. Now external forces is we have external forces how much? We have force is minus 10, let's put minus 10 here, and the moment is minus 15. And then Fx is minus 10, we have a distributed load, intensity is uniformly distributed load with intensity 10, this is 10. So this is the end of input. Now then the same thing we'll do, we'll initialize the global displacement vector, initialize the global stiffness matrix, and initialize the global force vector. Now once the initialization is done, then applied load Q, we need to find out the global this Q part. We know that there are two parts for the one part is this one and another part is the, you have concentrated load and concentrated move with the Q part. So this is the globalization of Q part, right? Okay. Now then boundary condition, this block is exactly same. So it based on the information we have provided here, it identifies the what are the points you have constraint and what are the degrees of freedom are constraint and what are the points we do not have constraint. So IDU will give you the all the indices of the point which are unknown, means which do not have any constraint, and IDUK will give you the indices of the points where the degrees of freedom are known. So means there are constraints provided at those points. Now this is the initialization of the, we have to, now this is the this is the initialization of these partitioned matrices. We have to find out those condensed equations which we can solve. This is the initialization of those matrices, sub matrices. Now next is computation of the global stiffness matrix and global global load vector, right? So this has to be done, this loop has to be over the elements, number of elements. Num LE is the total number of elements we have in the problem. I1 will give you the first node of the element and J1 will give you the second node of the element. So this element is connected between node number I1 and node number J1. Okay. So at node number I1 we have degrees of freedom. If we talk with respect to the local coordinate element coordinate system. So at node number I1 we have 1, 2, 3 and 1, 2 degrees of freedom. At node number J1 we have 3 and 4. So this is the length of each element, and then this is the element stiffness matrix. Then this is element load vector. We know that this this is the element load vector we have. Yes. So this is the element load vector we have. This expression already we had seen. Now then what we do is so then next is the assembling part. So this part is the assembling part. It's based on the connectivity. It assemble the the stiffness matrix, and then this is the assembling of the total load vector. So total load vector, this we have already first initialized with 0, then based on the information of Q we have populated F, and then now we have the information of Fe, information from the distributed force. So whatever information we had from Fe, now this information of Fe needs to be added to that. Okay, so this will be the total load vector. Now we have the global stiffness matrix and the global load vector. Next is the partitioning of the stiffness, these equations, and once we partition this and then finally we solve it, these steps are the same as truss. So this EU will give you the unknown displacement, and then once we know the unknown displacement we can use the second condensed equation to calculate the unknown forces. So this will give you the unknown forces. So once you know unknown displacement, unknown forces, just put this unknown displacement and the forces in the global displacement field. So this is the global displacement field. So U, once we see U will give you the displacement at all the degrees of freedom, at all the information about all the degrees of freedom. Now so then if we want to separate the transverse displacement and rotation. This also we can do. So this part, up to this part, is the solution part. Now once it is solved, next is we need to see the results. We need to see the deformation at various points. We need to compute the say moments at various points. We need to compute the deformation not just at the node, between the node as well. So let's do that. So now this is done here. So what is the expression for that? We have already seen here. These expressions are, this will give you the displacement at any degrees of freedom at any point within an element, and this gives you the bending moment at any point within the element. The same equation is written here. So these are the shape functions, and these are the second derivative of the shape functions required to compute the moment at any point. So your displacement will be the shape function and UV, and the moment will be the derivative of the shape function and UV. So this is stored in W1 and M for the transverse deflection and the moment. And the next we need to plot it. Okay. Now first what we do is, we will not plot it first. First let's highlight it. Let's see the result first. So U is how much? U is these are our we have used one element, so let us make it two elements so that we can compare these results with our manual calculation. Okay, so let's compute UU. Let's see the UU. UU is this, and let's see our result. Our results are, and this needs to be divided by EI, please mind. And our results we have here is, and this is our result. This 1 by if we divide it by 1 by 3, all this, then we will see this is the degrees of freedom we have. Unknown forces, if you see, the unknown force is 50, and these are the reactions we computed, and reactions already we had seen, the reaction is 50 and 105. So this is the results. The negative sign, it depends on how you take the sign of the moment. Okay. Now let's plot the deformed shape and the moment. First let's do it for one element. Let's do it for one element and plot it. Now, so first what I will do is, we will observe few things. Okay, I will make few changes here and there, and then just observe the change, observe the things, observe the plot, and then we'll discuss why, what is the reason behind all this. Okay, so this plot is for bending moment, this is for bending moment, and this is for deflection. And I don't know whether it is properly visible or not. I hope you can see these plots. Okay, so red one is the exact solution. Okay, what we can obtain from strength of material approach, and the black one is the solution obtained from finite element method. Now you see, if we plot, and the dots you see is dots are the values at the nodal point obtained from finite element solution. Now since in this plot we have just one element, so we have one node here and one node here, and then we have another node at the end, right? And then this one is the, let me plot it again. Yeah. So you see, yeah, here you can see the dot here. So you see the this point and then another point here, it will give you the total the deflection at the nodal point. Now this is the plot of bending moment diagram. Similarly, red one give you the exact solution, and the black one is the finite element solution. Now here we see that this bending moment diagram, they are not matching. Okay. Now, let's first remove this distributed load 0. We make this distributed load 0. Remove this moment also 0. Okay. Make this moment 0. So, this is the problem where it is a cantilever beam. We have only a load at the tip. Okay. How many elements? Still use one element. Now, let's plot the see this plot. This is the deformed shape of obtained from finite element and deformed shape from the equation, analytical results, and this is the bending moment. Let us see the error. We have defined an error like this. Error is here. An error is defined. This error is these whatever values you obtain from finite element, and we know the values, exact values, the difference and the percentage difference give you the error. Okay. And what is the error for this? You see, the error is, for this problem, it's 0. It is actually 0. Okay. Now, and which is again is very evident from the figure. We can see that the exact solution and the finite element solution exactly match. Okay. You cannot, just by looking at the figure, you cannot differentiate which one is exact and which one is finite element solution. Okay. Now, next what we do, next add this moment as well in this equation, in this expression. So, minus 10 kilonewton, and then moment also we can add, say the moment was 15, and then again run it. You see the bending moment diagram. This is the bending moment diagram, and this is the, this is the deflected shape, and this is the bending moment diagram. Exact match, and if we look at the error is still in the order 10 to the minus 12. Okay. And then, and this is obtained from just one element. Please note that. Now, next we add the distributed load as well, and then check. So, as soon as I add this distributed force, the results deviates. Okay, we see there is a deviation. There is a deviation in the bending moment. If we see the error is 1.6%. It is in percent. Okay. Why? What is happening if we add this distributed force? Now let us see that. You see, we have seen that at the nodal point these values match, and as I say, there is a reason for that. We essentially solve the same equation to determine the values at the node. But once we have determined the values at the node, then within the element these values are approximated through a shape function, and these are the shape function. Okay. Now look at what is the order of the shape function. Order of the shape function is 3. So this shape function for this is a cubic polynomial, right? Now look at the actual results. This is the actual result, right? So this is the contribution from this first part is the contribution from P, second part is the contribution from Q, and the third part is the contribution from M. Look at the expression for transverse deflection. The contribution of first part is cubic polynomial. Contribution of the second part is quadratic polynomial. But the contribution from the third part is fourth order. Now, our shape function is third order, right? Third order polynomial. We are trying to use third order polynomial to approximate a shape function which is based on third order polynomial, to approximate a polynomial which is fourth order. Right? Which is fourth order here. And therefore, some error is bound to happen, right? But whenever we remove this distributed part, and only the beam is subjected to tip load and the moment, our exact result is a cubic polynomial, and our shape function is also a cubic polynomial. So, if your shape function is cubic polynomial, then any force, if you have a force such that your solution is not cubic, solution is, the order of the solution is more than that, it is 4th order or 5th order solution, then some error is bound to happen, right? Now, how do I remove that error? How do I get the exact result? By increasing the number of element. Let's do that. Now, if it is one element, let's make it 2 element and then check the, you see, results are slightly closer. Bending moment diagram between two nodal point will be linear because our shape function is cubic, and in order to calculate bending moment we need to differentiate the shape function 2 times. So, distribution of shape function will be linear between two nodal point. Finite element solution, you can have a different expression, different curve for different curve obtained from the exact solution, but from finite element solution with cubic B-spline, polynomial shape function, bending moment between 2 points is linear. Now, this is relatively better. What is the error? Initially it was 1.6% and now it is 0.1%. If we further change it, make it 3, and then it is further closer. And how do I know it is further closer? We see the error. And if we keep on increasing the number of element, let's make it 10 element and then check. It is these, and then check the error. It is very small. If you can increase, you can use 20 element, you can use 30-40 element and see what happens to the error. Now, before we see how to plot this error, let's take one more example. This example is in this example, instead of we do not have P, we do not have M. Instead of a linear uniformly distributed load, let us apply a linearly varying load. Now, for uniformly distributed load, our expression is our exact solution is 4th order. But if your load is linearly varying, then the solution will be 5th order. Okay. So, if we implement this, now if we implement it and remove all other load, only it is linearly varying distributed load, keeping it is 10. Now, this will be the deformed shape. Let's take first with one element. This will be the deformed shape. You see the error, black one is the finite element and red one is the exact, and if you see the percentage error is 3.9. For quadratic, for uniformly distributed load, it was 1.6%, and here the error is more because our approximation is cubic, but our actual solution is 5th order. Okay, so that's why error is more. Now, if we increase the number of element and say make it 10 element and then finally check it, and we will see that error is very small. If we further increase it, let's make it 20 element and then error is further. So here we have seen that if we keep on increasing the number of element, we converge to the actual solution. Our error keeps reducing. Okay. Now, if we plot that, this is the plot for different 3 problems. So, the first problem is the solution is 5th order, second problem solution is 4th order, and the third problem solution is 3rd order, means cubic solution, and our polynomial is cubic. Our shape function is cubic polynomial. At the nodal point, we have seen our results are same as the strength of material, as the solution we get from the strength of material. It is between the two nodes within the element. What is the solution? We are interested in that now. Now, if we keep on increasing the number of element, we see that this is how this result converges. This is how the results, the error we can reduce. Okay. So, this convergence is achieved. This is how the error is defined for at least this problem, but this we will see different measures of error. Here the point is not to define any error measure, rather the point is to see how the result converges, how the error can be minimized by increasing the number of element. Okay. Now this is done by changing the number of element, or in another way we can say that by reducing the size of the element. Size of the element, we have now onwards, as I said, h h will be used to represent the size of the element. So this convergence is achieved by continuously reducing h, and that's why this convergence is called h convergence. There is another convergence which is called p convergence, but let us not bother about p convergence right now. We will see that convergence as well. So this is important. Now with this, let us stop here today. Next class, what we will do is, we have already done class problem, we have already done beam problem, and if we combine these two, we will get a frame problem. So next class we will see how to implement finite element method for a frame problem. Okay, thank you then. See you in the next class.